let's move on to the next part, which is collectives and non-blocking collectives. So if you used MPI, you've probably done some collective communication. So the idea in MPI is you have a group of processes, and they often need to do some kind of communication that can be done, they can do together. Maybe there is some process has data that everyone else needs, that is called a broadcast operation, or everyone has data that needs to be combined in some way with some arithmetic operation, such as a reduction, and many others. You could do all this on your own by sending all the data to one rank and doing the operation, or sending it to everyone, but you'd probably do it less efficiently than an optimized MPI implementation might be able to do. So that's why there are these functions that do commonly needed operations across a group of processes, and they're known as collective operations. They're widely used, and you should use them where you can and where they are useful. What collective means in MPI is that these functions, like pretty much all MPI functions, take a communicator argument. The communicator could be MPI com world, which means every process in the program that you've launched, or it could be another communicator that you have created. There are functions for creating communicators comprising a smaller group of processes. So collective functions are defined to be collective over the group of processes that are part of that communicator that you have passed to that function. And what that means is all those processes must call that function at some point in their program. If you don't, then the program can hang at that point. So if there is something else that keeps a process from ever reaching that function, the program will hang. So you have to be careful about that. These collective functions don't use a tag parameter. So normally an MPI send receive has a buff count data type, destination, and a tag. And then there's matching based on the tag on the other side as well. That's one of the matching parameters. The collective operations don't take a tag argument because they're supposed to be called in order. So if you're doing a broadcast on a communicator, all other processes in that communicator also must call that broadcast at some point, and then the matching is defined by the ordering itself. You cannot call a broadcast on one and a reduce on the other, on that same communicator. That's a program error. So collectives don't have a tag in them. MPI, until MPI 3, had only blocking versions of collectives. That is, there was no non-blocking collective. There was no I broadcast or whatever. That has been fixed in MPI 3. And we'll see that as well. Now you can do collectives in a non-blocking manner, similar to I sends and I receives. And collectives can be classified into three types: ones that do synchronization, ones that do data movement, and ones that do data movement and some computation associated with them. So for synchronization, the collective operation is a barrier. And the definition of a barrier is that a process will not leave the barrier until all other processes have entered their barrier, have reached their barrier. So if you do an MPI barrier on MPI com world, what that means is that no process can exit the barrier until all other processes have at least entered the barrier. So that becomes a synchronization point. So it doesn't mean that everyone exits the barrier at the same time, although they would be, because once they reach the barrier, very soon, once they figure out that everyone else has also reached the barrier, they would exit. But the definition as such says you cannot get out of the barrier until everyone has called the barrier. So at that point, you know the program state, that everyone has reached this function. But it is also true that in an MPI style programming, that is distributed memory style programming, a barrier is rarely needed, and Bill said this in the morning as well. You rarely really need a barrier in your program. But people tend to add barriers, particularly in large codes. They tend to add barriers just to be sure, or just to be safe. I've done a lot of stuff. Let me just call a barrier so that everyone reaches the same. that's not a good thing. You're unnecessarily adding synchronization, and Bill's the morning stuff also was about how synchronization can affect your program and add delays and unnecessarily. So particularly if you're running on tens of thousands or hundreds of thousands of MPI ranks, there can be some skew in the program. Each program runs at its own speed. There's no need to enforce a barrier somewhere, compulsorily. Of course, depending on your program logic, there will be synchronization points. So let's say you're doing collective communication that involves, that requires data from every process. Let's say you're doing an all reduce or something where every process has to contribute to the result. That is an implied synchronization point because everybody needs something that everyone else has to contribute. So that is an implied synchronization. Let that be there because that's an algorithmic requirement. But just adding a barrier to be sure or safe is not a good idea. And as Bill said, people have developed tools that you can use to actually go through your code and remove unnecessary barriers, or at least point out that the barriers are not needed. One legitimate use of barriers is for performance measurement. So you can use it just for that purpose and then comment it out or whatever. So in performance measurement, one often wants to measure performance in a way that everyone is starting from a known, at the same time from a known position. So let's say you want to measure the performance of some block of code. You could call a barrier before that code and then start so that everyone reaches that place at that time and then starts doing that in parallel. And so you call a barrier, you call MPI W time, you do that code, and then you call MPI W time again, and then you subtract that, and then you do either a max or an average or whatever is your method of calculating time. So that is okay. But then once you're done with the timing, you could comment it out, let the code run on its own. Is that clear? So one thing you could do is search your code for barriers and see whether they are really needed or not. If you're doing shared memory programming, not MPI, but if you're really allocating shared memory on a node, and there is a way to do it in MPI also, but which we'll see in the afternoon. But in general, MPI is not shared memory programming. If you're doing threaded programming, shared memory, there you need synchronization because there can be race conditions, and there you need maybe not a barrier, but other ways to synchronize, but not in distributed memory code. So avoiding barriers is a good idea. The collectives that move data, you're probably familiar with some or all of these. So there is a broadcast MPI bcast function which takes data from the root. The root can be any process, not rank 0. Any process can be the root, and gives the result to all other processes. Internally, MPI implements this in an efficient way. Typically, there are multiple algorithms inside. So depending on the size of the data that you're sending and the number of processes, it will pick the right algorithm. So typically, if it's a small amount of data, short, like this looks like a single element, it would use an algorithm. It would use some kind of a tree algorithm, a binomial tree type of algorithm to reduce the latency of the operation. If you're broadcasting a large message, it would use an algorithm that minimizes the bandwidth usage. So internally, for large messages, a broadcast is implemented as a scatter followed by an all gather internally. And that works out more efficient than a tree algorithm. And that's why I say use these functions, because the implementation is doing it more cleverly than the average user would. In many cases, it uses hardware features in the network. So the network might have some support for broadcasts or barriers or reductions. They get used, which you won't use if you're just emulating this above using sends and receives. So that was broadcast. There is also a scatter operation. So the scatter takes an array and effectively divides it among processes. It is not specified as a division. The way a scatter is specified is you specify the basic unit that needs to be sent, and then it sends the first element, the first unit of that to rank 0, the second to rank 1, and the third to rank 3, and so on. So you're like dividing an array and sending it. There is the reverse operation, which is the gather, which collects data from different processes and sort of creates a concatenated list on the root. Again, the root doesn't have to be rank 0. Then there are the all versions of these where everyone gets the result. In the previous one, you have to specify a root of this operation, and the root gets the result. In this case, the root is the sender. In the gather case, the root is the receiver of the operation. In the all versions, everyone gets the result. So this is by nature synchronizing, because everyone eventually has to wait for everyone to call the function, because they're getting some data item that everyone is contributing. So there is an implied synchronization here. Whereas in the regular broadcast, scatter and gather, there is no implied synchronization. So in a broadcast, typically what happens is that the root finishes the first. The root is done because the root has to just send data, and if it's sent in a tree-like fashion, it sends it to log p number of processes, and they forward it to others and so forth. So the root is the first to be done in a broadcast, and root will be merrily going on to whatever is beyond the broadcast in your code. It's usually the leaf element in the tree, the last process in that tree algorithm that finishes the broadcast last, because it gets the data the last. And similarly, in the scatter and gather, there is no synchronization. Whoever finishes first is done, gets the data, and goes ahead. So these are not synchronized. They're collective, but they're not synchronizing. And collective only means that everyone has to call the function. Everyone in that communicator calls the function. The all ones are synchronizing because you need data from everyone. So the all gather is everyone gets the same data. So everyone contributes one data item, and everyone gets the same result. The all to all is the most general and the most difficult to implement efficiently, because everyone gets a unique data item from every other process. So P0 has a unique item to send to 0, and a unique item to send to 1, and a unique item to send to 2. So this is harder to optimize. This is easy because you can create a tree that sort of forwards the data, and everyone collects it since it's the same data going to everyone. This is harder to implement. So if you can avoid using all to all, avoid it. But I know that there are algorithms where it's needed, and so there you should use it. So these are okay. So that was the collective data movement. There is one more which does computation in addition to movement, and that's reduction. And if you're application programmers, you've been using this. It's quite useful. So everyone has some data to contribute, but the result is not a concatenation. In a gather, it's simply a concatenation, one after another. In the reduction, there is some arithmetic operation performed on the data. So the result is also a single unit. If you're doing a sum, then this would be a plus b plus c plus d, and the result, whatever it is, goes to the root. The root can again be anything. Then there is also a scan operation, and the scan is similar to a reduction, except that everyone gets the result of the operations before it in the process rank order. So here, rank 0 will just get A, so nothing happens to rank 0. Rank 1 gets the result of A plus B, or whatever is your operator. It doesn't have to be plus. This one gets A plus B plus C, and so forth. So it's called parallel prefix operation. It's useful in some algorithms. There's also an MPI exclusive scan. This is the basic scan. The exclusive scan means that process's data is not included in the calculation. So that is also useful in some operations. So this is the list of routines. In addition to the basic the names that I had mentioned, there are these V versions of routines. So there is a scatter and there is a scatter V, gather and gather V. The V refers to vector version. So what that means is the size may not be uniform. If here it is uniform, everybody is getting one item, but if you have a variable number of elements that need to be sent to different, then it becomes a scatter V. where you pass a vector of sizes specifying who gets how much. That's more general. So there are V versions of scatter, gather, all gather, all to all, V. There is even a W version. Where is that? Maybe on the next slide, where even the data types can be different in the all to all. So again, MPI includes, it has everything in it. It's not a limited set of functions. So I covered all these. The all versions means everyone gets the result, and they become synchronizing. V stands for vector, and the reduction operations take either the arithmetic operations can either be any of a set of predefined functions, or they can be user-defined functions. So there's a whole bunch of predefined reduction operators in MPI: min, max, sum, product, logical, bitwise or, bitwise and a whole bunch of them. There's also a min lock and a max lock, where it's not just tells you the minimum and the maximum, but even the location of where the minimum and maximum are. And if that's not enough for you, you can also create your own reduction operation. So you can pass a function. You define the reduction function, and you pass it to a function called MPI op create. You pass it to MPI op create that returns an MPI op type that you can use in the reduction function. There are some rules on what you can do in that function or not. So it says that the user function is allowed to be non-commutative, but it must be associative. So what that means is that the basic data types that are the basic reduction operations are both commutative and associative. What that means is you can do the operation the operation could be done in any order. You could do an A plus B or B plus A. The result is the same. And associative means if you have a whole list of them, then you could do them you can do the brackets in any order, and the result would be the same. In the user-defined reduction operations, you're allowed to create a function that is not commutative. That is, A times B cannot be done as B times A. So that becomes a restriction. And often in the MPI implementation, the reduction algorithm that we use becomes less optimized if you pass a non-commutative function. But it must always be associative. If it's not associative, then it's a user error. You cannot. MPI doesn't allow you to do that. Is that clear? I mean, many of you are users of collective operations, I think. So is that clear so far? Any questions about collectives? Okay, so let's look at non-blocking collectives now. So this was added in MPI 3 for a number of reasons. One is to avoid deadlocks. So you could have, because collective operations are blocking and they must all be called in the right order by all processes, there could be cases where deadlock occurs if you're not careful. So that's one, and that even in point-to-point communication, if you're just doing blocking sends and receives, there is greater risk of deadlock if you're not thought through the program logic carefully. That's why you use non-blocking sends and receives. There is also the opportunity to overlap collective communication with computation. Collective communication can take some time because there are so many processes involved in it. If that could be overlapped, if that could be done in the background, you could save some time. There was also, between MPI 2 and MPI 3, there was like a 10-year gap. During that time, there was more knowledge gained about how to implement non-blocking collectives efficiently. So, for example, Torsten Höfler developed a library called NBC Live, I think, Non-Blocking Communication Live. That was not official MPI, but it sort of did MPI-like collectives in a non-blocking way, and he used them in some applications and showed that the performance was good. So there was evidence that this thing could be done efficiently. So as a result, it got added into MPI 3. So the semantics are simple, and it follows the usual MPI non-blocking send and receive semantics. So just as an MPI send has an I send, all the collectives have an I version. So there is an MPI I broadcast, there is an MPI I all to all and I everything. There is even a I barrier. So there is a non-blocking barrier, which at first glance doesn't make sense. That what is a non-blocking barrier? Because a barrier means you're waiting for something, but there is use for a non-blocking barrier. And if you are familiar with UPC, for example, the Unified Parallel C, which is a PGAS language, Kathy Ellick will talk about PGAS on Thursday afternoon. That has always had, since the beginning, it has always had this non-blocking barrier. They call it a split phase barrier. So what is a non-blocking barrier is the barrier is divided into two, an I barrier followed by a test or wait. So that's when the barrier is actually completed. So what that means is when you call an MPI I barrier, what you're saying is, okay, I have reached the barrier, but I don't need to know right now whether everyone else has reached the barrier. So you're just notifying everyone else that you have reached the barrier. In your code, suppose it makes sense to do other work before you really need to know that everyone else has called a barrier. Then that's what you would call an I barrier, do something else. And at the point where you cannot proceed without knowing that, okay, everybody has reached the barrier, that's where you would call the MPI test or wait to finish that barrier. So again, it's a way of deferring synchronization. It goes along, it follows that line. If you're running on a large number of processes, barriers, when they synchronize, they can take time. It's not the communication in part of a barrier involves some communication to know that everyone has reached. That doesn't take time. The time goes in waiting for everyone to reach that communication. So, and in a large system, you will encounter skew. Not everyone will be at the same place, and so you should use a non-blocking barrier if it makes sense in your code. If you're going to call a non-blocking barrier and immediately do the test or wait, that's not useful because you've not done anything in that time, right? You could as well call the barrier. But if it helps you, if you can do something based on your program logic, then it's useful. So, as I said, this non-blocking collective communication rides on top of the existing mechanisms for non-blocking communication in MPI. So you can call any of the test wait functions in the usual way. It passes the same type of request object, MPI request. So the semantics of non-blocking collectives are that the function will return. So what does non-blocking mean in any case? There is no time guarantee. It doesn't mean that non-blocking will return instantly or anything. What it means is both for point-to-point and collective, it means that this function cannot wait for or cannot its returning cannot depend on an operation happening on another process. So if you do an MPI I send or if you even are MPI I broadcast, it has to return purely locally. Return without depending on some operation happening elsewhere. So it cannot wait for communication from elsewhere, because if it did that, and if that other process did not reach that point, then it would block, right? Then that breaks the definition. So the same definition holds for the collectives, that if you call an MPI I broadcast, it will return without waiting for any remote operation. So now what it does, whether it does anything or not, is not guaranteed. That's a quality of implementation. So one acceptable implementation would be to do nothing in the MPI I broadcast. Just queue up that operation, and then implement it in the test or wait. That's not very efficient, but you have sort of deferred it and done it at the end. Typically, an MPI implementation would sort of initiate the communication when an I broadcast or I all to all or whatever it's called, and then later on it would try to do progress while you are doing computation or while you have called some other MPI function. So let's say later on you've called an MPI send that again goes into the MPI library. At that point, it could make progress on any outstanding communication in the past. So your previously called non-blocking broadcast is also being worked on at that time. And so that's how it's a mix of, you get your overlap of communication and computation. The restrictions are, again, there are no tags. The matching is in order, so you're still expected to issue these operations in order. You cannot call an I broadcast on one and an I reduce on the other. That doesn't match. On the same communicator, if you have different communicators, that's a different story. The other restriction is that when you have called the I broadcast, you pass the buffer to it, right? That buffer you cannot touch until you've called the test or wait. That's the other restriction. Another restriction is that, restriction or a good thing is that MPI cancel is not supported. Are you familiar with MPI cancel? So it's good. I would say it's good that you're not familiar. It's an operation we don't recommend as such. So avoid using it. So MPI has always had support for canceling non-blocking sends or receives that have been issued previously, right from the beginning. So what you can do is call an MPI I send, and then call MPI cancel to cancel that I send. And similarly, on the receive side, you could do an MPI I receive and call MPI cancel. And it's defined in a way that if the operation has not actually happened, then the cancel will succeed. If it is already completed, then it's not going to undo it for you. The idea behind cancel is that suppose your program is such that you don't know how many messages you're going to get. So that you posted a bunch of receives, and there is one of those receives tells you that, okay, I'm done. The sender is not going to tell you, it's not going to send you anymore. Then the other additional receives that you have posted, you could cancel them so that your program can, because at the end of the program, all your communication has to be over. I mean, you can't have, you can get an error at MPI finalize if you have not finished all your I sends and they have not been matched and completed. So that was the idea. I think the forum went a little ahead and even allowed canceling of sends, which is less useful. That you have sent, you've done an I send and then changed your mind or something. It doesn't make that much sense, but that was also there. It's hard to implement also, that one. So MPI implementers don't like that. But in MPI 3, the cancel is not allowed for non-blocking collective operations. You can still do it on the non-blocking point-to-point operations. So I think I've covered this stuff. I talked about non-blocking barrier already, right? I think I've covered all that already. So just to summarize, so non-blocking collectives are new, and I think not many people are using them. They're already supported. So MPI MPI 3 is available, as we'll see in the afternoon. The implementations exist. MPI-CH supports it. I believe OpenMPI also supports it. Most of the vendor implementations support the major features. There may be some arcane feature that they have not implemented. So this is available. You should try using it.
I would be curious to hear you haven't touched up on the topic of overheads of collective of IPcast and exemplary collectives, and when is it worth using it and when is it not worth using it, because with point-to-point communication there is likely a regime where it's simply not worth it. For instance, for very small messages or medium-sized messages and small amount of overlap possible.
You're talking overhead of non-blocking collectives or overhead of collectives in general?
Non-blocking collectives.
Yeah, so I would say you should use them when you don't need to wait on them immediately. And it's the same principle even for the I sends and I receives, that if you're going to call an I send, I receive and immediately call the test or wait, then it's not useful because you have effectively done a blocking operation there. If there's something you can do in the middle, in the meanwhile, then you're getting some overlap or something, then it's useful.
What's the amount of overlap that one can?
Yeah, so that depends on the system you're running on, and there isn't a hard number as such. presumably there is some amount of work in your code. Maybe you can do one more iteration of whatever is your compute that you're doing or something. If it's just a very trivial amount, then it may not be worth it.